Hello, so in today's video, we're just going to go through an important circle theorem, which will be important for the A-level maths course. So you would have actually probably seen this before in, earlier in school, high school, you would have seen this circle theorem before. So it's the fact that when you've got a cyclic triangle, so when you've got a triangle like this, ACB, trapped inside a circle whereby all the vertices, all the points are touching the circumference of the circle. And let's say that this AB length going from there to there is the diameter. So let's say you've got a triangle which has one of the sides being the diameter. Then it must be true that this ACB angle is 90. Okay, so yeah, the angle there. So let's just make a note of this actually properly. So AB is the diameter. So if AB is the diameter, then that means that the opposite angle to the diameter, this angle ACB, so angle A to C to B must be equal to 90 degrees. So that's the key circle theorem from here. So why would this be useful in high school maths, A-level maths? Well, if we think about it, if we just extend this BC line a little bit further across like that, if we extend this AC line a little bit further like that, so we know that these lines AC and AB are perpendicular. So let's make a note of this. So AC and AB are perpendicular. Okay, so they're perpendicular lines. So that means if we think about their gradients, so in the context of coordinate geometry, it means that the gradients are perpendicular, so they're the negative reciprocals of each other. So let's say the gradient of, so grad of BC equals M, then that means that the gradient of this AC line up here, so grad of AC, would be -1 over M, the negative reciprocal. So you could get a question where they perhaps give you the gradient of this A to C line, sorry, this B to C line. And then they could say, well, they intersect at this point C, and they give you the coordinates of that. Calculate the equation of this line A to C, and you can just use the fact that the gradient is -1 over this gradient there, and then you can substitute in your coordinates of X there, your coordinates of Y there, and get the equation there. So again, it's very similar to like the tangent equations, where you could be asked to find the equation of a tangent, because again, remember from the previous video, a radius and a tangent are also perpendicular. So let's say you got a tangent like that, so tangent there. Radiuses and tangents, or radii and tangents, I should say, are perpendicular. So again, you can use this negative reciprocal gradient to help you work out the equation there. Okay, so now let's look at how you would prove this circle theorem. So the proof of this, so the way you prove that this angle up there, again, I'll call this A, I'll call this C, I'll call this B. So the way you prove that angle ACB is 90 is what you're going to do is just draw like a line going from C to the center there. So what do we know? Well, we know that this, I'll call the center O as well. So we know that A to O must be the radius because it's half the diameter, because A to B is diameter. Again, let's just make a clear note of this. So AB is diameter. So because it's the diameter, therefore AO equals radius. We'll call that just R. Now we know also, O to C is the radius too. So like this here is the radius. So any line that goes in the middle to the circumference of a circle is a radius. So that means that we've got an equilateral triangle. Not equilateral, sorry, isosceles. So ACO, this triangle here, is isosceles. So that is the same as that size there. So we've got, let's just call this angle there X. Let's call this angle there Y. We want to find out this ACB angle. That's the objective. Let's just make a note of this here. So find ACB. That's kind of what we want to do in our proof. So we've got an isosceles triangle there. So if we've got the same size there R as the same size there R, then this angle up here must also be X there. So that must be X there. Okay, perfect. Now then, let's look at this triangle OCB. Now this is also an isosceles triangle, because again, that's the radius there. Going from O to B, that's the radius. Going from O to C, that's the radius. You've got an isosceles triangle. So if you call this angle Y degrees down here, this OBC angle, then this OCB angle up here must also be Y. Okay, so we now know that this angle, so therefore angle ACB B, so the one we want to work out, is x plus y. So this equals x plus y, because x there plus the y there. Okay, so we know that. Now then, we know that angles in a triangle add up to 180. So inside triangle ACB, we have angles of x here, x plus y up there, and y there. So x plus y plus y must add up to 180 degrees. Okay, so this gives us 2x plus 2y equals 180. Okay, so now if we divide both sides of that equation by the number 2, sorry, let me just make my writing smaller to fit everything on the page. Let's divide both sides of the equation by 2. That tells us that x plus y equals 90, but x plus y is also equal to angle ACB, so therefore angle ACB must be 90 degrees, and we've done the proof there. So yeah, that's how you would prove that angles in a semicircle, the angle in a semicircle is 90 degrees, and yeah, that's the key circle theorem to know. So again, angle in semicircle is equal to 90 degrees, and that is how we can prove that. And again, it's just worth bearing in mind that the lines at that point where we get the 90-degree angle, they're perpendicular lines. So again, we can work out the gradients if we're given one of the gradients.